welcome to the presentation with the title, Is the Commit Buggy? My name is Catalin Meirosu. I am Head of Systems Management at Product Development Group Software Defined Infrastructure at Ericsson.
I am Abgeiba Isunza Navarro, and I work as a machine learning engineer at Modulai.
And together we will be presenting on a new method for bringing AI into software development. So, is the commit buggy? When it comes to software complexity, people have to understand that a radio access network, which is what Ericsson is building in terms of infrastructure, is actually a very, very complex component. And just to have a term of comparison, in a radio access network, of which components you see here in the picture, and they look very much like boxes and antennas, and even more antennas on the other side of the picture, there is a significant amount of software that is actually being executed on these boxes. As a term of comparison, the amount of software that is that is developed by a company that does radio access networks is in the same order of magnitude as the software that controls the avionics of a Boeing 787 airplane. And a Boeing 787 has about 14 million lines of codes. And this is comparable to the amount of software that is being built for powering the 3GPP, so the mobile telecommunication standards infrastructure that is shown in the picture. If one actually adds the complete set of both boxes that handle the packets on the transport network, on the mobile core network, as well as the management systems that are attached to the network and see that everything has to run correctly, then one actually has a significantly more complexity in terms of software development, and the amount of lines of code actually reaches about in the order of 1 billion lines of code that need to be handled. Also, in terms of comparison, a lot of the equipment is actually running on Linux, just the Linux kernel. It's about 15 million lines of code. A database like MySQL has another 14 million lines of code. So it very quickly goes very complex. Today, about 99% of the code bases, including the ones that are part of telecommunication networks, actually contain open source components. And open source components are developed by people from all over the world in projects that bring them together to create software libraries that are being reused a little bit everywhere. Now, in terms of errors in that code, the software industry myth says that on average, 15 bugs or errors reach the customer for every 1,000 lines of code. Of course, in the telecommunication industry, this situation is significantly better, but nevertheless, there is a clear need for information and communications technology software vendors, as well as service provider, to control the way they take in open source software and ensure that there are as few bugs as possible, and also control the complexity of the software that they produce themselves, and ensure that there are as few bugs as possible in that one as well. When a software developer writes a part of an application, the commit is the operation through which the software developer actually stores that piece of code that they've developed securely in a software repository. Most of the software commits actually contain no bugs, but some of them may. And is actually very important that the number of the bugs that can actually reach a live deployment is reduced as much as possible. As just one example, the Openstack project, this is a very well-known open source project which builds software that powers the cloud infrastructure that is used by many telecom operators and many enterprises across the world. And we have looked at a number of versions of this Openstack project releases, spanning the time interval between 2011 and 2020. So 9 years of Openstack versions and commits. And we looked at really key parts of the Openstack project, like the parts that manage the compute resources, the storage resources, the network resources, as well as the authentication framework. And what we found is that from all the commits that were made between 2011 and 2020 in this particular project, about 87% of them were clean and about 13% of them were buggy. It's almost 47,000 commits. How do we know that these 13% commits were buggy? We know because throughout the years there were trouble tickets that were registered, and these bugs were fixed by the developers. Of course, there are a number of tools that developers use today in order to improve their output in terms of quality of the code. And these tools are falling within a number of categories. We have static code analysis tools and dynamic code analysis tools, and these are very well used. However, there are significant number of problems with the static code analysis and dynamic code analysis tools in terms of the amount of false positives, for example, that they are producing. And a false positive, it's a happening that actually creates additional load on the developer when a part of the code is identified as potentially containing a bug. And actually, it turns out after further analysis that there is no bug there. So one aspect that needs to be very much taken care of is reducing the number of false positives and identifying as many bugs as possible when it's still possible to fix them as part of the development process. And AI code analysis, it's groups a set of techniques that are very modern and that are starting to be used for addressing this type of issues.
So, as Catalin mentioned, AI is now used to analyze code and detect how many commits are buggy. And we perform a study to exactly solve this problem, detect how many commits are buggy and how many are clean in a repository. And for this, we study the machine learning technique called attention. Attention is a technique that was inspired by how humans have focus on parts of the information that are more important when there's a large amount of information in front of them. So, for example, right now that you're looking at the screen, you're probably focusing more maybe on the icons, on the letters, on the video, but not that much on the white background. So more or less like this, the machine learning models put more importance on those characteristics on an input that will help the model solve better the problem and predict the output that is desired. Attention has been very successful in natural language processing and computer vision, and particularly in natural language processing, the technique called transformers that use self-attention has pretty much revolutionized the NLP by having outperformed in many different tasks. And well, we found just natural that if these transformers architectures have been very successful on analyzing human-to-human languages such as English, French, Spanish, then they could probably work well on analyzing human-to-computer languages such as programming languages. So in our study, we studied two different attention technique. One was self-attention, as I mentioned already. This is used in the transformer architectures. And we also use another attention technique called bidirectional attention, which we apply between added and deleted lines of code to try to extract most of the information between them. So in this slide, you will look at our general system architecture. Our dataset is conformed by information extracted by each commit. In each commit, we have normally a code snippet that are change lines of code, either deleted or added. And normally, the developer will also submit a message that is generally in English, and that commonly it tells us about what the changes were for or what was changed in the commit. And in a first stage, we only use this information, and we extract the main characteristics using an attention network. And this attention network encodes all this raw information from the commit and represents it in a numerical vector. This numerical vector is then used as an input in a classifier network that will tell us if the commit is probably buggy or clean. In a further stage, we also use historical information from a repository that in this case we call repository features. And this is historical information of the changes that had happened before the commit that we're studying in that moment. So we collected around 14 different features. For example, some of them were how many lines of code were added at that point, how many lines of code were deleted in that commit, how many different files were changed, how many developers have interacted with those files before. And then we put together all these features that are represented already by a number, and we input it with the information that we extracted before from the code snippet and the commit message, and we use it as representing the information of that particular commit. We input to a classifier network that will try to predict if the commit might be buggy or clean. So what we found was that using this both information, one from the history of the repository, but also from the information that is input in the commit, so the code changes and the commit message is much more effective than the previous studies that will probably just use either one or the other. And also comparing to previous studies that were using other types of machine learning architecture, we found that attention-based models will outperform previous state-of-the-art in terms of accuracy and AUC. Among the two different attention techniques that we study, so self-attention and bidirectional attention, we found that self-attention is more effective as well. And among the self-attention, we study the BERT transformer architecture and also Roberta. And in this case, we found Roberta to be better with higher accuracy. We achieve accuracy around 86% and 0.77 AUC. Well, AUC goes from 0 to worse and 1 the best. We also did another study to see how our model will perform in a more real-world application. So we study if we could predict how many commits were buggy in a new release of software, given that we train our model on previous releases. In this case, we found that we had an even higher accuracy than in the previous studies, with almost 90% and 0.86 AUC. So we concluded that these self-attention transformers architectures apply to code, to programming languages, and in this particular case, to detect commits that are buggy, are effective to give us an overview of what's the state of a new version of software, if it's worthy to probably do an update on a software, or what is the state of this new software actualization. So we also think that obviously these models can be further improved, and one of these improvements could be that you use pre-train transformer architecture on code. By the time when we did this study, there wasn't any available, but I believe now there is. So this could be an improvement that could make even the system more accurate. Finally, as Catalin mentioned at the beginning, software architectures have become more and more complex, and it's important in our daily lives that we try to make more reliable software, and attention-based models are one tool that can help us find some insight of the state of our software in the commit level.
Mm-hmm. And our work actually demonstrates that AI-based code analysis may provide valuable feedback to developers, and tools that are based on this type of techniques could potentially be part of continuous integration loops in the future, and be really key in automating the quality assurance of software engineering.